Good morning all. In this video, I'm going to discuss about ideal operational amplifier characteristic. The outline to be covered in today's video session: ideal op-amp characteristics, op-amp open loop operation, op-amp with negative feedback. First, let us see the ideal op-amp. An operational amplifier is said to be ideal if it has following characteristics. Infinite open loop voltage gain, AOL is infinity. Infinite input impedance, Ri is equal to infinite. Zero output impedance, that is R0 must be equal to 0. It should have an infinite bandwidth, and common mode rejection ratio must be infinite. And zero offset, that is the output voltage V0 must be 0 for the zero input condition. That is, the differential input voltage is given by the difference between two input voltages. V2 minus V1 must be 0. And last one will be the slew rate of the ideal operational amplifier will be infinite. A slew rate is nothing but a change of the output with respect to the input. First, we'll see about the infinite input impedance. Since the ideal operational amplifier will draw no current at both the input terminals, that is, the current that has been entering into the input terminals of the operational amplifier is zero. It has an infinite input impedance. So, any signal source can easily drive the operational amplifier, and no loading effect will be occurring on the driver stages. And the second characteristic of an ideal op-amp is infinite open loop voltage gain, that is AOL is equal to infinity. Since the operational amplifier is having a or infinite open loop gain, it should give a finite output voltage V0 for the zero input voltages. That is, V0 is equal to AOL into VD, or the open loop gain is equal to output voltage divided by the input voltage. So here the input voltage is nothing but the difference between two terminal voltages VD. So in order to get since your AOL is infinity, to get a finite output voltage, your VD must be equal to 0. And third one will be zero output impedance. Since the ideal op-amp is having a zero output impedance, the output voltage V0 will be independent of the load current, so the output can drive infinite number of other devices. Our next characteristic is infinite bandwidth. Bandwidth is nothing but a range of frequencies over which this amplifier gain will remain constant, will give the bandwidth of this ideal op-amp. For the ideal operational amplifier, since the bandwidth is infinity, the operational amplifier will be giving a gain constant from the range of 0 to infinity. So this ensures that the gain constant over the range from 0. 0 is nothing but it gives a DC voltage level, that is 0 frequency to the infinite frequency. So this condition makes that the op-amp can be operated in both AC input as well as DC input condition. And next characteristic is zero offset voltage. As I already mentioned, zero offset voltage is nothing but an ideal op-amp will have a output voltage to be 0 for zero input conditions. So the presence of small output voltage, though V1 is equal to V2 equal to 0, is called as the output voltage. So for the ideal case, this offset voltage will be 0 for zero input condition, but practically that is not the case. Even if the input is equal to 0, you'll be getting some amount of offset error voltage at the output for the practical operational amplifier conditions. And next characteristic is infinite CMRR. CMRR is nothing but the common mode rejection ratio, which is nothing but the ratio of differential mode gain to the common mode gain. Since your ideal operational amplifier is having an infinite common mode rejection ratio, it ensures zero common mode gain, because CMRR is equal to AD divided by ACM. ACM is nothing but common mode gain. Since CMRR is infinity, your common mode gain is 0, which is nothing but zero common mode noise voltage can be achieved. Next, we'll see about the operational amplifier open loop operation. In open loop operation is nothing but without applying any feedback to the circuit. If you look at the operational amplifier open loop circuit, it consists of two input terminals and one output terminals, and the output is not fed back to the input. For such a condition, we normally call op-amp to be operated in open loop condition. So now we are going to apply two inputs to the open loop condition of the op-amp. Let V1 is the input applied to the non-inverting terminal of an op-amp, and V2 is the input applied to the inverting terminal. So negative indicates is the inverting terminal and positive indicates the non-inverting terminal of the op-amp. Then the output of a operational amplifier in open loop condition will takes only two values, plus V saturation level and minus V saturation level. So the output of this op-amp under open loop condition will take either high level or a low level. So this makes this op-amp to be used for only limited applications, like the operational amplifier under open loop can be used as an amplifier, act as a switch condition, or we can use it as a comparator application. So this limits the op-amp to be used for many applications. So in order to increase the utility of the op-amp, or in order to make this operational amplifier IC to be used for many applications, we are going to apply the feedback to the operational amplifier. So op-amp with feedback. So the type of feedback we are going to apply to this op-amp circuit is negative feedback, and this negative feedback has been applied in order to increase the utility of the op-amp or usage of the op-amp. And the negative, if you are going to apply negative feedback, the two conditions to be followed for the negative feedback condition. The first assumption we are going to consider is that the current that is being drawn by both the input terminals of the op-amp is considered to be negligible, that is zero, and the differential input voltage, that is the difference between two terminal voltages Vd must be always equal to zero. So these are the two conditions is being assumed if you're going to be used for the negative feedback circuit. And now let us see a very important, a basic type of a negative feedback circuit, which will be used for most of the op-amp application. The first negative feedback circuit is a inverting amplifier. Here the circuit diagram shows an inverting amplifier. If you look at the circuit diagram, here its negative feedback has been applied to this amplifier, that is the output from the sixth pin is being fed back to the second pin, that is the non-inverting terminal of the op amp. So the type of feedback we applied is here is a negative feedback, and why it is called as an inverting amplifier. If you look at the circuit diagram, the input Vi is being applied to the second terminal, that is the negative terminal of the operational amplifier, and to the non-inverting terminals we are not applied any input, it is being grounded. So since the input is applied to the inverting terminal, it is going to act as an inverting amplifier. So in such a case, the closed loop gain of this inverting amplifier, that is ACL, we can give the notation as AV or ACL. The AOL is the notation used for open loop gain of the op amp, and ACL is notation used for the closed loop gain of the op amp. So the gain of the op amp is given by output voltage divided by input voltage, which is given by minus RF. RF is the feedback resistor divided by input resistance, R1. Okay. So how we got this voltage gain is equal to minus RF by R1. We'll see in the next video session. The second type of a negative feedback circuit is a non-inverting amplifier. See, if you look at the circuit diagram, the input Vi is being applied to the non-inverting terminal, that is third terminal of the operational amplifier. So the output for this case is given by the closed loop gain, that is ACL, is equal to output voltage divided by input voltage is equal to 1 plus RF divided by R1, that is feedback resistance divided by the input resistance. So this will give the closed loop gain of a non-inverting amplifier. And the next feedback circuit is called as a differential amplifier circuit, where the input will be applied to both the terminals of the operational amplifier. If you look at here, the V1 is the voltage applied to the non-inverting terminal, that is positive terminal of the op amp, and V2 is the voltage applied to the negative terminal of the op amp, and we have applied a negative feedback. So the output voltage V0 for this differential amplifier is given by feedback resistor divided by input resistance, that is R2 divided by R1 into input voltage, the difference between two input voltages, that is V1 minus V2. So differential amplifier is nothing but the amplifier which is going to amplify the difference between two input voltages. That is called as a differential amplifier. So how we got the differential amplifier voltage is equal to R2 divided by R1 into V2, V1 minus V2. We'll see in the next video sessions. Okay, y'all. In this video, I've discussed about ideal operational amplifier and characteristics, and if we use the op-amp for the open loop conditions, what applications we can use, and if you want to increase the utility of the op-amp, we have to apply some feedback, and what are the basic feedback circuits we can use. The reference book followed is Linear Integrated Circuit by Rai Chaudhary and Said B. Jain. In the next video session, we'll discuss about the DC characteristic of an operational amplifier. Thank you.